Hi everybody, we're going to do N10 today, which is Introduction to Electrons. I love these quotes on the slide. The electron is a theory we use. It is so useful in understanding the way nature works that we can almost call it real. And will you understand what I'm going to tell you? No, you're not going to be able to understand it. I don't understand it. Nobody does. I like starting this lesson with these two quotes because there are probably going to be a lot of questions you're going to ask me about this stuff, and I'm not going to know the answer. And I don't think there's anything wrong with saying that. Some of the stuff regarding electrons and quantum mechanics and theory are so strange and so complex that even the people who come up with these theories truly don't understand it. And I think that's important for us to realize. So remember that, we're at a high school level chemistry class, and you can ask me questions. I'll give you the high school level answer. If you want to know a little bit more, I'm happy to explain a little bit more. But realize there are going to be lots of things that I just can't explain to you regarding how these electrons behave. If you ever take college chemistry, if you get a couple years in, you'll take a class called quantum mechanics. I loved that class. It's using a lot of math to explain a lot of the behaviors that we start to learn about in this lesson. So if you ever get to college chemistry and get a few years in, you can take that class and you'll learn a lot more. All right, let's get started. So remember the Bohr model of the atom. We learned about this one in middle school. So Bohr was the one who said that the electrons have to go around the nucleus in circles, like planets orbiting the sun, or maybe like rings on a tree trunk. But he was not correct. It's more appropriate to imagine them like bees buzzing around a beehive. The bees can go in all different directions, but they will tend to hang around the hive more than other places. And electrons are going to behave kind of like that. So the quantum mechanical model is going to be using some complex math to identify areas around the nucleus where the electrons tend to hang out, where the electrons are most likely to be found. The math is far beyond what we would do here. In college chemistry, we would do this math and it would fill up several chalkboards. So it's pretty complex. It's very interesting math, but it is beyond the scope of what we're going to do here. So Bohr talked about orbits, right? The orbits were the circles that he thought they had to stay on. But what we're going to be learning about are orbitals. An atomic orbital is an area where an electron is most likely to be found. Sometimes we'll call it a probability cloud. It's where the electron has a high probability of being. If we were to plot over and over and over everywhere we mathematically expect an electron to appear, we would start to see these three-dimensional shapes appear. And we call those shapes the orbitals. And it isn't that the electron has to be in this area, it's that it's just most likely going to be there. If I asked you, under normal circumstances, if we were at school, like a normal school day, and I asked you, where would your parents expect you to be at 11 o'clock on a Tuesday? The area you're most likely to be found in would be on school campus. It's not saying that you couldn't leave campus and go to your friend's house or walk down to Safeway or something like that. It's just that you're not, hopefully, likely to be found there. If your parents were trying to come find you, they're going to come to the school campus first. And so that's the idea here, is that the electrons don't have to be in these places, but they're probably going to be here. So you can see here, these little tiny blue dots are us putting a dot on the paper every single time we find an electron. And if we do it over and over and over and over again, you can see that this kind of spherical shape starts to take place. And that's telling us that most of these electrons are hanging out around this spherical area. So we call this an orbital. And you can see they just kind of estimated, okay, where would 90% of the dots fall? Okay, and they draw their boundary. But it isn't saying that you can't have an electron over here, or that you can't have an electron over here, or that it can't be down at Safeway down the block, right? It's just not likely to be there. So when we want to describe orbitals, we can describe them using kind of different levels of specificity. We can tell people the energy level, the shape, the orientation that the orbital points. Not all of them are spherical. Sometimes they're going to point in different directions. We can also tell people how many electrons are in each one. So one thing Bohr models are good at is energy levels. The energy level is kind of like the biggest, broadest category that we have, and Bohr got that correct. So energy level 1 is closest to the nucleus, 2, 3, 4, and it goes up to 7. Maybe someday we'll learn that there's energy level 8, but as of now we know about 7. The shapes of the orbitals have funny names because they're not really names, they're just letters. So there's an S orbital, a P orbital, a D orbital, and an F orbital. And same thing, maybe we'll learn about a G orbital someday, but for now these are the ones that we're going to learn about. An S orbital is spherical shaped. We just draw it centered around the axis. If I want it sketched out, make it look three-dimensional the best that you can. Don't just draw a circle. A P orbital, I was always taught that it was petal-shaped, like the petals on a flower. Sometimes people will call it dumbbell-shaped or peanut-shaped. I like petal-shaped because that's what I have been used to all these years. Inside an energy level, you can fit 3 of these. So you can have one pointing on the X, one pointing on Y, and one pointing on Z. So you can have up to 3 all fitting inside an energy level. Energy level 1 is too small. We cannot fit it inside of energy level 1. So you have to go up to energy level 2 before you can have any p orbitals. At the most, you can have 3 inside an energy level, X, Y, and Z. So we would say px, py, or pz. D orbitals are very strange. I would never ask you to draw these. There's 5 of them. In your notes, if you want to sketch it real fast, you can, but I wouldn't worry too much about it. They're going to look like double dumbbells, is kind of what I was always taught, double dumbbells, or dumbbell with a donut around it, okay? So those are some D orbitals. You can see the shapes are getting more complex, and we're getting more of them. F orbitals, we say, are funky shaped. You can see they start getting really weird here. We have like 2 donut things here pointing different directions. We got spiky ones down here, all sorts of crazy things. Same thing, I would not ask you to sketch all of these F orbitals for me. So talking about the orientation, an S orbital does not have orientation. It's just a sphere. It can't point a different direction because it's totally symmetrical. The P orbitals have X, Y, or Z orientation. I don't care which you label X, Y, and Z. Just make sure that you're consistent. Remember, these are 3-dimensional, so we can rotate it. It's not a big deal if you label differently than I do. D orbitals and F orbitals are a little too complicated for us to do their orientations. You have to start learning things like planar geometry. We're not going to do that, okay? So the only one I would ask for an orientation on would be a p orbital. Next, let's look at how many you can fit inside an orbital. You can fit 2 electrons in each orbital before it's full. One is spin up, one is spin down. We are not literally talking about the electrons spinning like a top. It's not like one goes clockwise and one goes counterclockwise. This is a pretty strange phenomenon that has to do with magnetism and things like that. You learn a little bit more about it perhaps in a physics class or a quantum mechanics class. For us, we're going to just have to focus on the fact that we can have 2. The first one we put spin up, the second we put spin down. And after that, it's full. It's going to also kind of come down to some math that we're not going to get into as well. We do use arrows to represent the electrons. We'll draw up arrows and we'll draw down arrows. So if you want to tell somebody where an electron is inside an atom, we can describe it in a very similar way to how we would give somebody a mailing address, okay? So just go with me for a minute. This is a silly analogy, but I do think it helps, okay? So think about where you live for a minute, okay? If I just ask you, hey, where are you from? Depending on, where you are, who I am, why I'm asking you, you may be giving different levels of answers. If you're on vacation in Europe somewhere and somebody says, hey, where are you from? You may say like, oh, I'm from California. Most people know where California is. And then they say to you, oh my gosh, that's where I'm from actually. I'm on vacation too. Where in California are you from? And they say, oh, I'm from Pleasanton. And then the person goes, oh my gosh, that's where my grandma lives. Where in Pleasanton do you live? And then you say, oh, they live on, I live on Ferdinand Avenue. And the person goes, oh my gosh, that's my grandma's street. Which house is yours? Then you would give them the house number. Now, in real life, I hope you're not giving your address to strangers, right? We have to remember, identity theft and all of that. Who's this weirdo asking for your address? But the idea is, depending on what you're doing and what you're trying to describe, you can get more and more and more specific, right? You can write an address for where you live. If I need to mail you a letter and you tell me your address is California, that's not super helpful, right? You have to have more and more levels of specificity to get what you're really after, which is to know exactly which house you're talking about. Well, we can do the same thing for an electron. So we can write an address that tells us exactly which electron we're talking about. So kind of going along with this analogy a little bit more, the state would be the equivalent of our energy level. The city is the shape of our orbital, S, P, D, or F. The street would be the orientation, which direction is it pointing, which orbital am I talking about? Am I talking about the PX, the PY, or the PZ orbital? And then inside that orbital, we can get even more specific and tell people, is it spin up or is it spin down? If you give people all of this information, they will know exactly which electron you're talking about. They will know exactly where it is inside that atom. So let's look at what one of these would look like. We do a big number in front, and that would be the energy level. So this is in the second energy level. We do a lowercase letter next to tell us the shape, the type of orbital. We do a little subscript to tell us which direction it's pointing, which of the p orbitals is it. This time it's the x orbital, the px. And then the last is the spin. +1/2 would be spin up, minus 1/2 would be spin down. And once again, don't worry about the math behind that. That's just the notation we'll use, plus 1/2 minus 1/2. So this tells me that the electron is in the second energy level inside a p orbital. It's the p orbital that's pointing along the x-axis, and it's the electron that is currently spin up. Now I know exactly what I'm talking about. Now, I don't know about you, but I really don't need to know all of this information about every electron inside an atom all the time. You know, if we have 118 electrons, I don't want to have to write this out 118 times, one for every electron. The spin is so complicated, we are not going to usually care about that. And same with orientation. So what we're really going to care about for the most part is just energy level and the shape. So I'm going to show you how to write like a shorthand version of this to shrink it down so that we can write these much faster, since we really don't care about all this complicated stuff. So this is a configuration for an atom. You would say this as 1s plus 1/2, 1s minus 1/2, 2s plus 1/2, 2s minus 1/2, 2px plus 1/2, 2px minus 1/2, etc. That's a lot to write out. So let's try to chunk it and put all the like terms together. So the first chunk that we're going to combine are the 1s electrons. We're just going to lump these together. I don't care if it's plus or minus 1/2. These are just going to get lumped together. Next, the 2s. Same thing. I don't care if it's plus 1/2 or minus 1/2. I'm just going to lump them together. Next, remember we don't care about plus 1/2, minus 1/2, but we also are not going to care about the orientation. So I'm going to lump all of these together. So I have 2 electrons that are inside a 1s orbital. I have 2 electrons inside a 2s orbital. I have 6 electrons inside a 2p type of an orbital. So what I can do is I can shrink all of this down to this little tiny electron configuration down here. So I would say this as 1s2, 2s2, 2p6. You're going to hear that we kind of have a rhythm to it. The rhythm is purposeful. Our brains latch on to the rhythm, and so you'll be able to memorize the pattern and how we say these much better if you can kind of practice the rhythm and actually say it out loud. I know that feels weird to sit there like chanting these little electron configurations, but it is very helpful. And when you do that, you're going to internalize it well enough that you will notice if there are any mistakes in one. So it's a great thing to practice out loud. So if you want to describe where all the electrons are, right, we just shrink it down to the basics, the energy level, the shapes, and then use a superscript to tell people how many electrons you have. So for example, 1s2, 2s2, 2p6, 3s2, 3p4. Now I can use these configurations to figure out which atom I have. If I have 2 electrons here, and 2 here, and 6 here, and 2 here, and 4 here, I can add them all together. I can see that I have 16 electrons, and now I know that it's sulfur. I look at my periodic table, I find the element that has 16 electrons, and I know that it's sulfur. So we can use configurations to identify atoms. So we're going to go over the steps today, and then next time we'll actually start writing these ourselves, but I do want to just kind of outline the steps on how to do this. So what you're going to do is pick an atom. You're going to find out how many electrons it has. You're going to start putting the electrons into something called an orbital diagram or an orbital chart. So this is going to tell you the order that the orbitals come in. Unfortunately, they don't always go in the order you would expect. So this is going to tell you what order they go in. And then you list off which orbitals you used and how many electrons were in each one. That's what gets you the 1s2, 2s2, 2p6 thing. This is what the orbital diagram looks like. You have one as a reference sheet in the front of your 3-ring binder. There's also going to be a little glue-in that you can print for tomorrow, for the next lesson, that will be this printed out, and you can draw in the little boxes. We're going to put little arrows into these boxes, and that's how we're going to figure out where the electrons end up. There are going to be some rules for how you know where the electrons go. You do have to know the rules by name. That is something we expect because they are so important, and it makes it easier to communicate and talk about them. The first is Aufbau Principle. So the Aufbau Principle says that an electron occupies the lowest energy orbital that it can. And what that means is we're going to fill from the lowest orbital up to the top. Fill from the bottom of our chart, energy level 1, and fill upwards. I like to remember it in a silly way by saying electrons are lazy, right? They're going to do as little work as possible. They're going to use the lowest energy orbital possible. The next is Pauli exclusion principle. The Pauli exclusion principle says no two electrons in the same atom can have the same set of 4 quantum numbers. So quantum numbers are all of those pieces of the configuration. It's the energy level, it's the orbital type, it's the orientation, it's the spin. So quantum numbers are how we represent the address in a mathematical way. We don't cover quantum numbers anymore. Even in AP chemistry, they don't do quantum numbers. In college, you'll learn about quantum numbers. So it's basically how can we take the configuration, the address, and make a mathematical equation out of it. So his principle is saying that you can't have 2 electrons with exactly the same address, okay? They can't have the same exact quantum numbers or they would be the exact same electron, and that's not possible. You cannot have 2 electrons that are literally the same. So if one is spin up in the orbital, the next must be spin down. Otherwise, they would be the same electron. The next one is one that's a little bit hard to understand until we start using our orbital diagram. So we're going to talk about it now. It may not make sense. After the next lesson, we'll come back and we'll look at the definition again, and I think it will click. The next is Hunds Rule. So what Hunds Rule says is that orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. Kind of a mouthful. What it means is that if there are more than 1 orbital at the same energy level, you're going to put 1 electron in each before you pair them up. It takes a little bit of energy to pair the electrons, spin up and spin down. They don't want to have 2 negatively charged objects next to each other inside the orbital. They would rather have their own elbow room and spread themselves out. So the analogy I like is imagine that your parents have a house and it's a 3-bedroom house. And your parents take 1 bedroom, you get 1, and there's an extra. And you're an only child. And then they go and now you have a sibling. So now they have 1 bedroom, you have 1 bedroom, and now your little brother has their own bedroom. You're not going to want to share with your little brother if you don't have to. If there's a bedroom available, you're each going to take your own bedroom. Well, now they go and have another kid. So now your parents have a room, you have a room, your little brother has a room, but where's your other sibling going to go? Where's your little sister going to go? So somebody's going to have to share, right? Somebody's going to have to partner up now that you're out of space, okay? So let's go back to look at that picture of the orbital diagram. Here we go. So do you see here, these p orbitals are at the same energy level? I'm going to put one electron in here, px. I'm going to put one in py. I'm going to put one in pz. And now they all have their own bedroom. And now they're going to have to double up if there's more electrons. So now it's going to be px again, then py, then pz. Now they all have 2. They're all full. Now I go up to the next level. So what we'll do is we'll practice putting electrons in these little boxes with our arrows. And when we get to something like the p orbitals or the d orbitals, or way up here you see the f orbitals, we will have to spread the electrons out, and then we come back and then we double them up. Everybody wants their own bedroom before they have to share. Okay? And that's it. So we will practice with our orbital diagram. We'll get good at that. And then when we're good at that, I'm going to show you a trick on the periodic table. Because believe it or not, the periodic table is set up in such a way that it has all the information you need to write a configuration for any atom that exists. Okay? So we can't teach you the trick right away. We tried that once. It did not go well. Okay? So I think if we can practice with the chart, then you'll be able to see the pattern on the periodic table much better. And in our experience, we've been doing this for many, many, many years, all the teachers together at Doherty. And, it does go better if we practice with the chart first. So my motivation to get you to do your practice and to learn the chart really well is that I will promise to teach you a shortcut with the periodic table once we get to that point. All right. Bye, everybody.